Alright guys, welcome to this page of the notes, and again what we're doing is we're graphing rational expressions, graphing rational functions. And I've got another one for you right here. We've done a few of these at this point, so let's just go ahead and jump right into it. Again, I kind of give you a roadmap based on the boxes below, the things I need you to find. So let's go ahead and jump right into it by doing that. Here we go, X-intercepts. Well, we know we can find X-intercepts by setting the numerator equal to 0. So my numerator is an x to the fourth minus 16. Okay. Well, I take a look at this, and again, we have seen this over and over and over again in this chapter. This is a difference of squares. X to the fourth is a perfect square, and 16 is a perfect square. So we will factor it as a difference of squares. I will get x squared plus 4 and x squared minus 4, right? That's all equal to 0. Zero product property lets me split those guys up and solve them separately. So x squared plus 4 is equal to 0. X squared minus 4 is equal to 0. Here we go. X squared is equal to a negative 4. Take the square root of both sides. Guys, please notice, I'll be taking the square root of a negative number. Oh yeah, that's imaginary. But 4 is a perfect square, so I get plus or minus 2i. Alright, so I wind up with imaginary zeros, but fortunately I'm not done. I still have this x squared minus 4. So let's see what happens here. X squared is equal to a positive 4. Okay, alright, this one works out alright. Take the square root of both sides and I get plus or minus 2. Okay, so here's what happens. Right now, at this point, I have 4 x-intercepts. 2 of them are imaginary, which I can't graph, and 2 of them are real. We'll see if they're actually x-intercepts. Remember, if they show up here, then it's actually point discontinuity. But for now, we'll say, all right, it looks like I have 2 real x-intercepts, one at positive 2 and one at negative 2. But we've got several other pieces that we need to kind of get in order to see what this puzzle kind of looks like to get an idea of the picture. So let's keep going. It's very interesting, but let's keep going. My denominator is an x squared minus 1. Again, this is a difference of squares. I wind up with x plus 1, x minus 1. So we'll split those guys up, set each of them equal to 0. X plus 1 equals 0, which means x is equal to a negative 1. X minus 1 is equal to 0, which means x is equal to a positive 1. So it looks like I have 2 vertical asymptotes. I have vertical asymptotes at x equals plus and minus 1. Now, again, we've seen this before. 2 vertical asymptotes is not that big a deal. It certainly can happen, right? 2 vertical asymptotes, it can happen. So right now, it looks like, well, actually it doesn't look like, we've just confirmed, right? The only way it wouldn't is if the same values show up in both of these boxes, but they don't. So I now know I have 2 real x-intercepts, plus 2 and minus 2, and I have 2 imaginary, so just ignore those. They don't show up on our graph. We can't graph imaginary numbers. And I have 2 vertical asymptotes at plus 1 and minus 1. Interesting. Very interesting. All right, here we go. Let's find ourselves a horizontal asymptote, if there is one. Ax is equal to, well, the degree of the top is 4. The degree of the bottom is 2. Well, that means that the degree of the top is greater than the degree of the bottom. This is rule number 1. And that rule number 1, it just keeps showing up. Just keeps showing up. No horizontal asymptote. Instead, we have a slanted asymptote. So that means we're going to be doing either long or synthetic division. Hope synthetic works, but I don't know. We'll see. Let's see what happens. All right, so we come up here. I take a look at my rational expression, and will synthetic division work? Well, remember, 2 things have to happen in order for synthetic division to work. The first thing that has to happen is the leading coefficient has to be a 1. Check. The second thing that has to happen is the variable must be to the first power. Oh, bummer. So synthetic division will not work because I have an x squared in the denominator, and it only works if it's an x to the first power. We have to do long division. You don't have a choice. Also, this one's interesting because I am missing powers of x. Please notice I have an x to the fourth, but there's no x to the third, there's no x squared, and there's no x to the first. You need placeholders. Also, please notice, in the denominator I have an x squared, but I do not have an x to the first. You will need a placeholder. So don't forget those placeholders when doing long or synthetic division. Here we go. My divisor, the denominator, put the placeholder in there. So it's going to be x squared plus 0x minus 1. All right, so there's my divisor. My dividend, right, is this guy, but I need my placeholders, right? So it's going to be x to the fourth plus 0x cubed plus 0x squared plus 0x minus 16. Okay. Now, I know it looks scary, but take heart. Look at all the zeros in there. Zero is a really easy number to do math with, so actually I think this one's probably going to go pretty quickly. Well, I don't know, let's find out. Remember, 4 steps to doing long division. You will divide, then you will multiply, then you will subtract, then you bring down. We don't care about the remainder, doesn't matter. So, divide first, x to the fourth divided by x squared. Well, x to the fourth divided by x squared is x squared. Make sure you line up your powers of x. Since I get an x squared, it will go over top of the x squared. So there's my x squared. That's step 1, divide. X to the fourth divided by x squared gets me x squared. Step number 2 is to multiply. X squared times x squared is x to the fourth. X squared times 0x will be 0x cubed, right? Add the exponents. 2 plus 1 is 3, so I get plus 0x cubed. X squared times the negative 1 will be a minus x squared. That's step 2, multiply. Step number 3, subtract. Don't forget to distribute the minus sign, so I'll put that guy in parentheses. Check that out. X to the fourth minus x to the fourth, those cancel each other out. 0x cubed minus 0x cubed. Those guys drop out. 0x squared minus a minus x squared, that turns this into a positive, right? 0 plus 1 is just an x squared, so 1x squared. So we get x squared. Bring down. Actually, you can bring them both down. Plus 0x minus 16. Why did I bring them both down? Well, this is a trinomial, right? I'm going to need to subtract. So this also needs to be a trinomial, right? I need the same number of terms here as the number of terms that I have here. So I know step number 4 is to bring down, but I actually got to bring both of those guys down. Here's the good news. There's nothing left to bring down, so I know after this next round of division, multiplications, I would wind up with a remainder. But I don't care about the remainder, so we're actually almost done. X squared divided by x squared is a plus 1. Plus 1 is a constant. Please make sure you put it over top of the constants. Right there, plus 1, and I can stop, right? Remember, I stop because 1 times x squared is x squared, 1 times that is 0x, 1 times that is a negative 1. I do my subtraction. That number I would get would be my remainder because I have nothing else to bring down, but I don't care about the remainder, so there's no point in continuing to go. My oblique asymptote is at, remember, the quotient is your oblique asymptote. It's y equals, is that y equals x squared plus 1. And I love this because now we get to go back to chapter 4 where we graph quadratics. This is an x squared. Now remember, when it comes to quadratics, y equals a times x plus or minus h squared plus or minus k. Well, this is our general form for the transformations of a quadratic function. My a would be a number out front of the x squared, which in this case is just a 1. So there's no vertical stretch or compression. It's not flipped over the x-axis, right? There's no reflection or anything like that. So a is 1. H. Well, if I had an h, it'd be inside parentheses with the x, but I don't, so that means h is 0. There's No horizontal transformation. There isn't one, and my h is 0. So then what is this guy out here? Well, that plus 1 tacked on the end is a k. That means that it is the x squared function. It's just the parent function shifted up 1 unit. K is plus 1. And that will be, I know we call it a slanted asymptote. It's actually not a slanted asymptote. It's going to look like a parabola, but it is still a line that my graph will approach but never touch. Interesting, interesting. Okay, here we go. Back down here real quick. Did I have anybody show up in both the x-intercept and the vertical asymptote box? I didn't. So when it comes to points of discontinuity, there aren't any. All right, guys, time to put the pieces together and see if we can come up with a graph. Here we go. I had x-intercepts. I had 2 imaginary, which I can't graph. I had 2 x-intercepts, one at plus 2 and one at minus 2. Let's put both of those on there. There's plus 2 and there's minus 2. Okay, great. Then my vertical asymptote box tells me that I have a vertical asymptote at plus 1 and minus 1. So let's put both of those in there. Huh, that is really interesting. All right, so vertical asymptotes. I got my vertical asymptotes in there. I've got my x-intercepts in there. The last thing I need to do, right, is my horizontal asymptote, which I don't have one. It turns out that my other asymptote is going to be this quadratic function, x squared plus 1, and we already talked about it. It looks like a parabola. It's just shifted up 1 unit, right, because k is plus 1. So that means that that guy, I'll do it in a different color so you can distinguish it, starts right here, right, at plus 1, and then it's going to be a parabola over 1, up 1, over 1, up 1. If we go over 2, over 4, 1, 2, 1, 2, 3, up 4. If I went over 3, that would be up 9, over 3, up 9, over 3, 9. All right, so it's going to run right through there. Again, I'm making it a dotted line because while it doesn't look like the other slanted asymptotes we found, it still represents an asymptote, represents a curve that my function will approach but never touch. All right, guys, let's see if we can put these pieces together. I am not allowed to touch the red dotted lines or the green dotted lines. Can't touch those. I have to get really close to them, but I cannot touch them. And the kicker is I have to go through these points, right? It has to go through these points. Well, the only way that works, the only way I can get really close to this line and get really close to this line and go through that point is if it looks like this. Right like that. And the only way I can get really close to this line and really close to that line and go through that point is if it's kind of the mirror image on the other side and goes like this. All right, so this one is a little different than the other rational expressions, rational functions that we have looked at, but again, still a really great exercise on finding x-intercepts, vertical asymptotes, horizontal asymptotes, or a quadratic that is a line that we can approach but not touch, and then of course points of discontinuity. Again, if you're taking this class with me, I don't need to give you anything crazy like this to figure out if you know how to do the algebra, right? So if you're taking a quiz or a test with me in this class, all right, I'm going to give you something that'll look a lot more like the reciprocal function, where you've got that general shape that we're familiar with from the reciprocal function, but I'm going to be looking for you to do all of that algebra. And absolutely, you may need to use the quadratic formula to find your x-intercepts. And you absolutely may have to do synthetic or long division to find a slanted asymptote. All of that stuff is fair game. Right? You need to be able to do it. And again, the more practice you get, the better you'll get at it and the faster you'll get at it. Guys, I love graphing rational functions. I hope you had a great time. I can't wait to see you in the next couple of sections where we move on with this discussion on rational functions. So much fun. I'll see you next time.